welcome to the September PDH Hour with Glenn. I'm your host, Glenn Tepfer, and today we're going to be looking at material interface types and their impact on destructive sample failure rates. I'll give you a brief outline here, and I'm going to start with an introduction, some of the questions that needed to be answered in my mind from working out in the field. Then defining the weld interface for those of you that may not be familiar with it. Project data, I did a study and my coworker, field manager, Brent, we put together a paper and presented it at Geosynthetics 2019 on this subject. But yeah, you only get 15 minutes or so to present, and people have been talking about this issue, and hence the webinar. I think there'll be a lot more detail in here than you can give in 15 minutes in a speech at a conference. So the project data, what defines a failure rate, there's different ways of looking at them. Examination of failure rate, so the different material interfaces. And then what was quite astonishing is a tracking revelation that I like to share with everybody. Then we'll move on to the current guidance practices and really for your destructive sampling, the guidance for original sampling and then tracking. And, there's some things that definitely need better practices. We'll look at failure analysis. Why did these samples fail? We'll look at why textured material is harder to properly weld than a smooth material. I'll give you some recommendations, brief conclusion, brief introduction to the next webinar, and then questions and answers. So if you can use the question and answer feature on your browser at the end of this webinar, I'll try and answer those. I should have time. So a couple other reminders here. Any of the past webinars can be found on our website. You can use this QR code, and PDH hours can only be awarded to those who attend the live webinar. So that's the only way we can somewhat hold people accountable that you've been here for the whole hour. So, all right, with that, we'll get into the introduction. And, I was on a job, this is a job maybe 2017, I think, and we had a lot of failures, and most of them I noticed were based to the textured interface. And so I thought we should look into that. So we went back through some of our projects. This particular project, I think we had about 1,500 lineal feet fail. It was a 15 to 16 acre project. And these are all fusion wedge welds, by the way. And so, yeah, there was an astonishing failure amount on this project. And so I decided to look into 7 historical projects that we did. Like I mentioned, Brent and I did the presenting of the paper material interface types impact on destructive sample failure rates back in 2019 in Houston. You want to take into account the goal, a goal of a containment system is to contain, and that lies in the details, constructability, the technical specs, CQA plan. But one of the things that's often overlooked is weld interface, and no one really talks about that. There's a gap in the industry in their guidance that I believe needs to be addressed. And then I wanted to examine the question, what impact does this interface have on weld quality? And we'll get into some results of the 7 projects. And, they did show that there was considerable volatility on any interface that contained textured material. And then that leads into the importance of interface in your destructive sampling plans. So defining the interface, there's multiple types of interfaces. We typically describe it in our nomenclature as the top sheet over the bottom sheet, or with a slash there, smooth slash smooth, smooth slash textured for smooth textured, and textured with a T/T. I used this cross-section here from another presentation of mine, actually, just to illustrate what we're talking about here in the interface, you have your top sheet of material, your bottom sheet of material. The weld interface is going to be where those two materials come together to be welded and joined together. And we're talking about, materials on projects that vary. So if you have just a smooth or a textured, no overlap of those materials. I didn't really study those in this paper. This is where you have the smooth welding edge on a textured material. So you end up with all these different combinations, smooth, textured, smooth, textured, and textured. And looking at a project, one of the considerations, I believe, is that, why aren't these sampling of interfaces performed much? I think, a lot of it's hit and miss. If it falls in your 500 feet, 1,000 feet, they'll be hit, but they're not really targeted. And these seams, you can see they add up. I colored in, highlighted different colored seams here. These purplish colored ones were textured to smooth, so you have that along your tie-in and some other seams. And the installer, did a good job there. They put down their floor panels and they deliberately and intentionally put the smooth welding edge there, so they were only welding one textured component instead of two textured components together. And I think they did that because they get better quality welds. Then you have your textured, the smooth, and the yellow, or not yellow, the other color there. I can't see it on my screen very well. Yeah, the orangish one up here is your old along the tie-in. And then the blue is a tie-in of texture to texture. That's the old sheet to new. And then you had the blue or the yellow being texture to texture, new to new. And then all the other seams that you see there are just regular smooth to smooth. So you can see that the footage adds up. Then, like I said, this is about a 15 to 16 acre cell, and there's quite a bit of seamage footage. And as I go through the paper and the discussion here, I'll refer to these as secondary seam interfaces. So if you see that in any of the slides, I'm talking about the smooth, textured, anything with a textured interface. Smooth was the predominant welding on this project. And just for those of you that may not be familiar in the field, a few slides here to kind of illustrate them. Here's a corner where you got your smooth edges of a textured panel. So you have smooth, and then you have a textured, and textured smooth up here. Actually, you can't see it, but a few more photos will show it. Your smooth of a textured butt seam. This tie-in, like I said, was textured over a smooth welding edge there. You can't really see the smooth, but that's what it was. Your smooth out on the floor. And this is more of a close-up where you can actually see it along the slope there. Then another photo here showing the same thing basically, except that this material in front of us there, the lighter material, it's the same material, but it was flipped over. And the engineer approved it, said the interface wasn't a problem, but we pointed that out during our CQA that the installer was flipping the material over, and there are different friction angles. So if you ever see that, you need to question that. All the manufacturers say there's different friction angles between their upper and lower sides of the sheet, or top and bottom sides of the sheet. So that's something to keep in mind, especially for the interface friction testing, and then how those results correlate in the field if it's not installed properly. So that was kind of a side note, but what really got me to thinking were the amounts of these large caps on this project. And you can see here they're capping another fusion welded butt seam tie into each other there. So getting into the project data here. Oops, there it goes. All right, I think I'll get the keyboard working correctly here, but yeah, over seven, or we looked at 7 projects, kind of an overview here. There was the project selection criteria, as I mentioned earlier. There were multiple interfaces, so it wasn't one that was just smooth, or textured. It was one that had the different combinations of materials. The projects were both caps and cells, so you had, I think it's two that were LLDP and the other five were HDP. They were 40 and 60 mil. Project size varied from 5 to 125 acres, and the climate diversity, some of these were in the southeast, the southwest, the midwest, so they were all over the United States, installed in, summer conditions, typical summer conditions. The installers were diverse, so different levels of experience. The design, the design is one of these things that you get your panel layouts from the installer to improve. You can look at those and see if there's ways to minimize these secondary interfaces. You may not need to be stuck with as much of these seams if you look at the design from or the panel layout from the installer. And yeah, the secondary interfaces on all these projects were 3,000 feet or more. So the project data, like I mentioned, we only picked projects that had multiple interfaces, but failure rates, I figure we're talking about failure rates. I'll take a moment and discuss that. There's a ton of ways to calculate out failure rates. You talk to installers, they'll be calculating it out a different way than you are, most likely. But the way I did it, I took all original samples were included where they were passing or failing. And then the failures, what they included were field screening of the original samples, field screening failures of record tracking samples. So if the installer did their own QC, which is the last bullet there, the installer did their own QC on their tracking samples, they might, cut 5, 6 samples thinking they have a passing area, and they don't. And they cut each one of those. I didn't record them unless they called it, a sample that was ready for the laboratory, a sample of record. Laboratory failures, obviously, the originals, and laboratory failures of the tracking samples. So those were what's included in the rate. And I know there's different ways of calculating it, like I mentioned. So looking at the project data here, and I'll get into a little bit of this more detail. I've broken up some of these tables so they're easier to see. This table shows you the different amounts of welding and really the percent that was smooth, percent that was textured, and the percent that was smooth. And you can see some of the projects didn't have all of the same interfaces. And this one shows the different failure rates. And like I said, I'm going to break this up so it's easier to see. This was a table presented back in 2019. So breaking up the table, looking at the overall results, the overall failure rate, if you looked at the overall failure rate for the different projects, it was anywhere from 3.7% to 9.4% with an average of 5.4%. Now, the industry, you'll hear all the time, failure rates are 1 to 2% typically. But, like I said, there's a lot of different ways of calculating them out. What do those rates actually take into account? One thing they don't take into account a lot of times is these actual on-site samples. So laboratories are usually only getting the final result. You go through screening, things fail, they're not going to be recorded by the laboratory. So you'd expect that the laboratory numbers may be a little bit lower. But 5% still a reasonable expectation in the industry, I believe. I know we can do better on jobs, which we did. This table here is just breaking up the failure rates cumulative by the different materials so you can compare them. The first project, number 1, had a 0% failure rate on the smooth, and project number 6 had a 0% failure on the smooth textured. So the 0% is possible, but you can see the difference when you look at the different interfaces here. You have your smooth, it's only 4.4%, but then you get into your textured interfaces and you're somewhere around 11%, at least on these 7 projects that we looked at. And so we break it up even more, I thought, well, it'd be interesting to look at it um, in terms of how much of the welding of each type of material was performed on a project. So for this one, we had the smooth. 72% of the welding was smooth. So, that's pretty good. Overall, 91.4% of all the welding was smooth throughout the project study. And it had a failure rate of 4.4%. Then you get into the textured to textured, and we only had 3 projects, unfortunately, that had this interface out of the ones we had data for at the time. And you can see that they averaged a failure rate of about 10.8%, and they ranged anywhere from 8.1% of the total welding to 28%. And, taking an average of the whole project was 3.1% out of all the 7. If you're looking at it cumulatively for all 7, if you're looking at it for only those 3 projects, it was 12% of the welding. And so you have, a reasonably small amount of welding, but it has a fairly high failure rate of 10%. Um, and you'll see the same thing really with the smooth textured or textured interface. We have average of 11.4% failure rate. Like I showed earlier, 1 project had a 0%, but the failure rate went up to as high as 25%. And if you look across all the projects, it was 5.6% failure rate. And if you only look at the ones that had the smooth textured, it would have been 7.5. So you have a fairly small, it's about half the amount of textured, and well below what the smooth is. So it's a small amount of welding, but yet it's failing at, double, triple or more the rate. And then what's highlighted here in pink really is um, problematic too, but there were no requirements for it. But there was 751 feet welded of the smooth textured or textured, whichever was the case, but we didn't take any destructs on that project. And it encompassed 0.7% of the total welding. So you had some, 750 feet. We should have at least had 1 or 2 samples on that, but it was missed, and it was missed as a result of the protocols and not being required to test it. So it was acceptable, but seeing these failure rates, it definitely is something that I think should have been targeted. So then I thought, well, let's look at how much footage the failing footage encompasses. The destructs failed, you tracked them. So how much footage did each failure amount to? And the different footages are summed up here in the table. You can see the different. We had 90 feet to 1,000 feet. You're going to get a variation on different projects and the number of failing samples and everything. But when you looked at the failing footage as a percent of the total welding for that interface, um, the smooth is only 0.5%. And you look at textured, and it's 2.7%. And then you look at the smooth textured combinations, and you're up to 1%. So what that's really telling me there is that you're getting your smooth failures. You find a spot, but it's going to bound pretty quick. It's going to bound and pass. The textured, any textured interface, on the other hand, is going to propagate more. So your failure is going to, run a little bit longer. It's not going to just be bound, 20 feet, 10 feet in each direction from your failure. More than likely, when you encounter one of these, it's going to propagate further. So that's, another finding to keep in mind, and another reason behind my ultimate recommendation of, targeting interfaces. Kind of a summary here. Some other information too that's pertinent is the testing was done in accordance with ASTM D6392, and the results were compared to GRI GM19. Back then it was GM 19, now it's 19A as the reference for whether they passed or failed. Again, industry standard failure rate, 5% or less is typically what's acceptable. But we were seeing failure rates, 3.7 to 9.4% on these projects, and failure rate average across all the projects was 5.4%. So looking at them by the material, we talked about these. The smooth averaged 4.3, textured averaged 10.8, smooth textured smooth averaged 11.4. But when you look at these in total, the failure rate of any textured interface is 250% more likely to happen than on the smooth. Um, but yet, we're not always targeting these. So I'll get into the failed sample tracking here. I'm going to go back to that same drawing I presented earlier to illustrate the issue here. And what you have here, if you look, what I did is I put the green arrows and then a number 1 as to what seam they welded and what order they welded them in. So number 1, 2, 3, 4, 5, those were the different seams that were welded. The first seam would have been 83, 81. That would have been 83 being on top, 81 because the sump is down here. That's the direction it would have been welded. If you ever want to figure out the overlap, stand facing down the seam. If your left foot is on the lower sheet, you're facing the way the welders here in the United States run. So this order here, they welded 1, 2, 3, 4, 5, and you can see the different interfaces. So say I came along and put a destruct number 1 on 83, 82 here. Now that's a textured butt seam there. Well, if we track it by conventional recommendations here, standard protocol is going to say we go to the seam welded after and the seam welded before, provided that whole seam fails. So the after would go on to seam 3, which is 84, 82, and it would go to the beginning of that seam for the chronological pathway. And that's going to be a smooth interface. And same thing with it before you go to the end of the previous seam, it's going to be seam 1, 83, 81. And again, it's a smooth interface. So odds are that those are going to pass. It's just the way it is, and I'll show you more on that here in a little bit. Maybe next slide or a few slides here, but so those pass, so now we're done, right? Everybody says, okay, we're all happy, we have them bounded, but nobody considers seam 4. It's another textured seam that this guy welded, and he might have had the same issues on that seam, or he came down and he welded this whole tie-in here, and nobody's sampling that now. Nobody's considering it because we got the destruct here, it's bounded, when in fact all of these other seams should be suspect, and it needs to be thought about and addressed as part of your protocols. And here's what happened. We did look in the study when we tracked 2 alternative interfaces, and projects 1 through 3 each had textured samples that were tracked onto a smooth sample. And there were 4 samples for which this was the case. Each time they tracked back to a smooth interface, they passed. There were no failures when they tracked back to the smooth. Same thing with the smooth and textured interfaces. We had 3 projects with that. And we had a total of 8 samples, and all 8 of them tracked to smooth interfaces eventually. And once they reached a smooth interface, they passed. So that really raised a red flag to me. It's really kind of eye-opening. I think we're tracking things in the wrong direction, or, we're not taking into account similar material interfaces that have failed. We're going chronological, and that was always the belief that, something goes wrong with a machine, you go chronological and you have it fixed. But I think this data shows otherwise. You may not have it fixed. You really got to be evaluating it by interface. And kind of another note on that, we were working on a cap, and And I was around the same time, maybe a year or two later, but we're working on this cap and they're doing the 40 mil LL, and you have a lot of butt seams on the cap, and they do the 45, and you have your textured interface. And I brought this up to the engineer. I said, we're failing on these butt seams. Should we evaluate more? Increase our sampling, make sure we increase that. And he said, no. He was fine. And then I asked, well, what about, having the installer do end coupons where at least they can check the texture on each seam? We're not cutting a sample. And he didn't want to do that either because it's not in the specifications to do. And, then the owner chimed in that he wanted a, B minus job. He didn't need an A plus because it was a cat. So, the things happen, a bit frustrating when you deal with them. And, you like to get to the bottom of the issue and make sure that owners have a good quality job at the end of the day. So with that, I'll get into some current guidance, and how I feel it's lacking. What's the current guidance for destructive seam sampling? Excuse me. So the industry guidelines primarily are found, within GRI protocols. There's some the basic 1 per 500 feet. There's different credit given to who first came up with that. I know JP Giroud's name has been thrown out there as far as coming up with that, and in talking to JP, I know he was one of the first people that, referenced it. And he did say that, um, he only threw it out there as a general guideline for something back, when the industry first started in the mid 80s or so, somewhere back in there. It wasn't meant to stay as a standard. It needs to be evaluated. So people are trying to evaluate it. And that's what you get here from GM19. A actually offers two other guidance documents. GM19A is um, one that you check your seam integrity results against. But it recommends GRI GM14 and GRI GM20, which I'll get into in the next slide, as well as possibly reducing the amount of sampling with the electrical leak location. And so, like I mentioned, you have your fixed interval, 1 per 500. Then GRI GM14 uses variables, and it basically is meant for projects that are over 100 samples, a minimum of 30 to start. And basically, both of these practices, you increase the spacing between your destructive samples based on good welding results. So you can jump up from 500 to 750 to 1,000. I think maybe 1,000 is the max on it. GRI GM20, similar principle. You're rewarding good welding, and that one can be used on projects of just about any size. And then, another practice, leak location surveys, reducing or not doing destructs altogether based on that. That's one that makes no sense. My question here is, where's the interface? Interface isn't discussed in any of these protocols when you look into them. Oh, yeah, I'm trying not to go down the rabbit hole of leak locations replacing destructs either. I'm going to go there for a split second just because, it's one of my pet peeves in the industry, and I continue to see it, and it just frustrates me. It's non-destructive testing, it's leak location. It's not a substitute for integrity testing. They don't correlate. It's not the same thing. It's just frustrating. It's a big pet peeve of mine, but I'm trying to get this out there, so that's why I left it in here. But just think of a sheet of geomembrane. All right, say you have a sheet of geomembrane, 60 mil thick. You're going to do a leak location survey on it. You got a conductive medium behind it, either on the sheet itself, so conductive backed 60 mil, or you have a conductive subgrade below. Take a knife and gouge it 50% of the way through. Gouge it, 30% or 30 mils. That 30 mils isn't going to reach the conductive lining of the geomembrane or the conductive sheet. It's not a hole, or I mean the conductive subgrade. So it's not a hole. So you're not going to get an arc. It's not going to detect. Take a tensile test of that. I can guarantee you, you're not going to meet your properties on the material. The two do not correlate. Um, so, all right, I got to get myself out of that rabbit hole here. Uh, all right, back to destructive sampling here. So the practice is summary. There is no guidance on interface specific sampling. And, trial seems ironically have guidance. Most of the CQA plans I see say that they need to be tested trial seams per operator and machine combination per interface. Your textured, smooth, the interface. And that's pretty standard on, most of the CQA plans. Occasionally that's not there, but pretty common, but yet nobody tests the destructs and targets the destructs in that same manner. And I think part of it has to do with the belief that it's such a small percentage of the welding. But, as the data we showed there, small percentage can have big implications. So standard tracking, basically, most of you probably know this, but you go 10 foot in each direction is pretty much your standard tracking process when you have a failing sample. But I think there's a better practice, and don't know why. I think I'm back here. Yeah. All right. I'm trying to make sure I'm not getting ahead of myself here. My keyboard's stuck here. I apologize for that. Um, but a better practice for overall sampling, really. This one isn't necessarily even dealing right now at first here with the um, tracking samples. I'm really looking at your original samples, and I did this in a previous webinar. I forget which month, but you can find it on our website. It was a two-parter on destructs. And you could see what I did is put the intervals, and I really specifically used this welding machine combination AS and W wedge 65, and showed his pathway of seaming, and the different colors highlight the different 500-foot intervals. Now, in the old days, we'd have these destructs marked per the blue stars, and you just wheel off 500 foot, and wherever it fell, that's where you marked a destruct. And you'd miss the interfaces that way. You'd miss operators sometimes that way, machines. It wasn't a very good way of doing it. So it kind of evolved to what is mostly done now is people will look at the machine and operator combination, and they'll track it per 500 feet. So you look at the yellow again, wheel off 500 feet on his seaming, and you take a destruct at the red stars. Do that for your next interval and wherever the red star is. And that's typically what a lot of engineers are doing. But now you're cutting holes needlessly in the liner. I say needlessly, you need to meet the requirement, but you're not really gaining knowledge. It's just a random crapshoot. I think if you're cutting a hole in the geomembrane, you need to be using it to discern something of value. Try and make sure that the quality is there. And so you can do that, and you can also minimize holes if you look at the whole 500-foot interval, out to the red star in each one of these. But then you examine it, and are there suspect areas in there? In this case, there's some burnouts, and I would take a sample somewhere where the yellow stars are at. So you're hitting all these suspect areas. You can hit the interfaces. You can hit all the different interfaces for each welder. So when you look at it, suspect areas that I thought were suspect, I'm able to hit 3 out of 3, keep it in my sampling frequency. Texture to textured interfaces, I was able to hit all 3 of the different combinations, and I still kept it in my 1 per 500. And I didn't put any extra holes in the geomembrane because I took them where there were already existing holes were going to be. I just think that's a better way of doing it. And, that's a way that it can be done, I guess, that I think can help, and you can get your interfaces targeted. Um, and this is really pretty much a summary of it, directly on the weld path. One thing is the balanced sampling here I mentioned is you have failures, you get a wedge or an operator, combination, they're failing, and you have your 1 per 500 foot or 1 per 1,000, whatever it may be. I've always used flexibility, like at Palo Verde, when we were welding out there, the zero leak project. If I had an operator machine that failed, um, I would just reduce the frequency or target him more. I might reduce him down to 350 feet, but I'd increase each of the other operators 50 feet or 75 feet to help accommodate for that. So at the end of the day, I had the same amount of samples, but I was able to target the guy that I had a question with. And you can do things like that. None of these things are set in stone, and the owner really liked that flexibility that I did, and everybody was happy with it. We got a good quality project and eliminated a lot of failures. But um, you know, a lot of people take these guidelines as written in stone, and you have to do them, and they're not. You can have variance within them. So with that said, I'm going to move into the failure analysis here. Um, what we've seen, the failures in the study. Uh, excuse me. So failure types, all of the failures were peel test failures. We didn't have any shear failures in this study. Still see shear failures every now and then with fusion, more so with extrusion, but for the smooth interface, the peel mostly were peel adhesion, but some had low strength. Textured interface, again, peel adhesion, but some had very low strength with a textured. And that's one of the, another thing that I like to warn people about, because we tested at Palo Verde and other sites. We tested our samples on site, and I would run the tensiometer and do the testing in the climate control. And you'd see where you start getting a peel. You might get that peel at 10%, or I mean, 10 pounds. The requirement's 91 pounds. For strength, it's starting to peel. It peels 10, 15%. At 10, 15 pounds, maybe it goes up to 20 pounds or something, then the peel stops and it gets its strength and it exceeds the strength. And, is that good? Is it not good? I don't know. I'm not an engineer, but, I'd see people and engineers that would say, okay, we had 25% peel, but we had our strength, so I'm going to pass it. And I've seen them, back when it was 4 or 5, they'd pass it with a spec was 80% of the strength. But where did it start to peel? A lot of times it starts to peel at a low pounds and it just gets up there. Sometimes it's even the squeeze out that gets the strength. So that's kind of another tangent there. I got a lot of tangents I can go down, so I'll try and stay on track here for you. Um, the importance of the diagnosis, don't just repair, find a root cause. Um, you start getting multiple failures, you need to really identify what's going on so you can keep from the problem propagating. If you can get it under control, then you can avoid it in the future. Heat, speed, pressure, and moisture and dirt are common ones, but sometimes there's material issues as well. And then, obviously, dirt was a big one for smooth. If it wasn't dirt or cleaned, we had a lot less failures. Dirt seemed to be present quite a bit. Texture, a lot of times that's dirt. We'll get into dirt later. And then poor heat penetration. So why are textured materials more challenging to weld? I wanted to get into this really. I think it ties everything together. Excuse me. Um, whoops. But getting into the actual welding, so kind of a lesson. Some of you already know this, but you have three main things, and this is a magic triangle as called or described by Eddie Weiser, who shared this with me from Leicester. But your heat, speed, and pressure, those are your three components in thermal welding. For any material, you're going to have a window that, you'll pass these peel and shear, but you'll have a nice sweet spot where you're getting the best quality weld possible. But I think it goes further than that, and people don't realize that too. You need your heat, speed, and pressure, but you need a good foundation. And that good foundation is being clean and dry geomembrane interface. And so you definitely need that. I'll touch on that here in a few slides. But how are heat speed and pressure accomplished. With the thermal fusion welding, some modern ones, it's all the speed is a machine setting, the heat's a machine setting, the temperature of the wedge. You have your wedge here. The liner comes in, gets warmed up, goes through the nip rollers that put the pressure on and form your final bond. And um, you have your pressure. And there's a difference in machines, and a lot of people don't realize this, but you look at this diagram, and this diagram for the Pro Wedge by Demtech really explains how you set it up. You know, it's not a calibrated um, instrument that you can just dial in the pressure in now. There are machines out there that you can do that with. Leicester has some that have direct readouts of pressure, but these machines didn't at the time, and I don't know if they've developed anything with the pressure on them or not. I know they have data recorders that get pressure, but you look at it how it's set up, and it's based on the thickness of the sheet, and that's key there. Your nip rollers have to be, set up based on the thickness of the sheet, and same thing with another one of their models. It's the thickness of the sheet, and you get into the instruction manual, and they say, quote, the correct amount of nip pressure is needed to get a good weld. And it goes on, and then it gives six step instructions about adjusting based on the sheet thickness and such. And then you get into, final note, and it says when pressure adjustment is set up correctly, it should engage and should take some effort, but it should feel like a smooth motion. And sometimes you see people struggling with it to get it to clamp down. Is that correct or not? The trial weld's passed, but does that mean it's a good weld? That's a whole different issue there, but it doesn't mean you're getting the right pressure. But it even goes further than that. Um, but here's another warning. I'll get into that other statement. It goes further than that here in a moment. But keep in mind that the thicker the material being welded and especially textured, the greater the pressure should be. So that's really what I'm getting at is, okay, you set it up for um, a textured material that's thicker, and then you're going back to welding a smooth material. Can you be using the same machine? Should you be using the same machine? I don't know, but here is an example of the different thicknesses of material from the cut sheets from Agdrew and Solmax, and you can see the nominal thickness 60 mils. It averages 57 mils for their 60 mil microspike. And then the asperity height, the thickness of your texturing above that base 60 mil sheet is 20 mils. And similarly, with the Solmax product, 6057, it's typically going to be that because I think that's the requirements for GRI GM 13 for HDP or 17 for LL, but your asperity height is 16. So you got different thicknesses, and you look at the smooth, that's pretty uniform. You look at textured, and you can see how the thickness, all these spikes, the asperity height there, that's all pressure against a machine that it's got to be compensated for. So the thicker your material, the more pressure it's going to take to get a good weld. Excuse me. And this table here was just showing the different values of the material, basically from the cut sheets at the time. 2019 when this was put together. I don't know if they've changed much since then. But the thickness implications, I put together this table basically from the last one. You have your 60 mil smooth, 60 mil single-sided textured and double-sided textured, and you add in the asperity height to your base sheet, and you're up to 97 mils of thickness just for one sheet. So if you add that to your base there, you're at 120, with two sheets of smooth. But then your asperity height comes in for your single-sided textured, your double-sided textured, and you're up to 194 mils, 198, 178. And that's 150% or greater than your welding for your smooth material. So does that make a difference? To me, it's hard to understand how you can do that with the same machine and not make any pressure adjustments and just go from welding textured to smooth and back and forth, and then some textured smooth textured interfaces in between. It just it's something I question, and I haven't really been able to get a definitive answer out of it. But I remember in the old days, there would be a dedicated machine for textured material, and a dedicated operator too. Even at Palo Verde, that was 2009 to 2012 or 13, they had one guy that was predominantly responsible for welding all the textured welds out there in one machine. So, maybe they know something about it. Um, just something to keep an eye on. I don't have all the answers, but part of it is I like to get people thinking about these things, so I'm not the only one laying awake at night losing sleep. um, so you could see here in the study, there was no readout, like I said, to measure pressure. So the only thing we could look at is their settings, ambient temperatures. Typically they run faster. They kept the same heat and ran faster with a smooth than they did with a texture. And that's quite common in the industry. And that's what you're gonna, commonly see. So um, get on to really um, the other factor, the foundation, the heat, speed, and pressure. We just talked about that. But, cleaning, keeping it clean and dry, cleaning, it's more difficult on the textured geomembrane. Excuse me. Um, with all the asperity height there to catch the dirt and debris and whatever it may be, mud's especially hard to get out of there. You almost have to wash it, and nobody wants to wash it. And then you have the geomembranes wet, and people don't want to deal with it being wet either. Um, but also, once it's wet, you got to dry it. And in this case, you can see here, this was after a rain event, and they're going to weld this butt seam here. It's a textured to textured butt seam, and I was surprised it came back passing on the destructs. But what they did, they had to get it clean, and then they had to dry it, and they used the heat gun, or commonly called Leister in the industry. Excuse me. And they held it at a distance and dried out the geomembrane, and they did a good job. The destructive samples passed, and they looked pretty good. That was several years ago. And then, another thing you're always going to want to keep an eye on and see are they cleaning the machine? After every seam, they should be taking a brush to the contour rulers and making sure things are clean, that the dirt's out of there, the nip rollers too. And if you don't see them doing that, a lot of times you'll see it results in failures that could have been avoided. I've seen it more than once where they don't take the time to clean. And I think the thickness overall gets into one of the issues with um, what you see, going through the intersections. People will weld through the intersections, and there's two schools of thought. Europe, I guess it's a pretty standard practice. It is here in the United States. Everybody likes to weld through the intersections, grind them down, weld through them, and do a long continuous air test. But one of the people that used to work for the manufacturers back in the day told me that he thinks it's a bad practice because in his experience, machines loosen up internally. And so you get all that pressure, you're going through that intersection, you're so thick there, almost 200 mils or whatever the number was earlier, just for your two sheets of overlap if it's textured, but then you throw in a third or a fourth sheet there. That's a lot of pressure, and you're trying to have that machine go through and maintain that pressure. Something's got to give. And unfortunately, a lot of times, the equipment, I think, does loosen up over time, and it results in failures that could have been avoided, and particularly when you're dealing with the textured interfaces. But any multiple intersections like that, um, my recommendation follows his. I don't recommend welding through it. I think it's you're you're rolling the dice and potentially increasing the risk of other problems. So with that, I have my recommendations basically. Always ensure the foundation for good welding, clean and dry. I mean, that's what, the installer is supposed to do. That's what we're there for as CQA. Risk assessment, I think up front, everybody should be evaluating material interfaces. Make sure it's part of your destructive sampling protocols. Make sure the installer knows that. Figure out in the design or, the approval process, how do you minimize the amount of these um, secondary interfaces? Excuse me. Like I said, look at the installer's panel layout. There may be ways to do it. One way used to be the 34-foot sheet. We used that at Palo Verde. I'm not even sure that that's even available in the United States anymore. It used to be produced by GSE, but I haven't really followed what Solmax has done with the 34-foot wide sheet, if they still produce it on demand or not, since buying that out. But clear specifications, have it in all the different plans. Have it in your CQA plan that you're going to test the interfaces, the tech specs if you put them together. It can be done, and again, it can be done without harming the liner. Like I said, on that B minus project, I suggested end coupons. That's another way I think you can test these interfaces without taking a destruct there. But you have an issue, make sure the installer's pulling end coupons and testing the 1 inch coupons to see if those textured interfaces or smooth textured interfaces are good. Then you can, maybe avoid some laboratory samples. There's already going to be a hole there, so you can take advantage of that. There's different ways to do it, different strategies you can implement, and I think that's important that something's implemented. Monitoring the weld parameters, obviously the temperature, speed, pressure, and that needs to be done. You need competent CQA. That's one thing I left out about the failure rates. We at CQAS often have higher failure rates than other people because we do it differently. We do the interval, we try and use it to the best of everybody's advantage, help us learn from it, ensure the quality while we're doing it, and not create more holes in the geomembrane. Thorough review of failure. I think that's critical, and that really gets put by the wayside. People say, okay, yeah, sample X failed, sample Y failed, and they track them, and everything's good, but nobody looks at them. Is it the same machine, same operator, any of that type of criteria? People need it's not hard to put it in a spreadsheet and actually track it. Is there trends? You can look for trends, see if they're barely passing. That was one of the things I did when I was testing my own samples in the laboratory. Is I'd see things that were close to a failure. They didn't fail, and I let the installer know, hey, you were lower than normal here. And we save failures. There's no doubt we save failures by having that knowledge to the installer. And same thing. It could be easily be put into tables. Um, yeah, I had another thought on that, but I think it left me. Sorry. But I think you have to review the data and look for those trends. That's what I was going to say about the trends too. Look at the trends. One of the projects we were auditing, I start looking at it and I look at the fusion welding, the extrusion welding, and I see that this one operator failed on every piece of equipment he ever touched for trial welds. Now he passed his destructs, but it was random on that project whether they were hitting them. They weren't targeting them, and wasn't really good CQA oversight. When we were out there doing our audit, they were being more influenced by where the installer wanted the samples taken than what they should have been. Um, but yeah, the guy failed everything he ever touched. He should have been sampled. He shouldn't have even been allowed to weld potentially. I mean, extrusion weld, wedge welders, different equipment. You look at the paperwork, he had failed on everything. But that's a whole different topic, and again, another rabbit hole. So I'm climbing back out there. Conclusion. The industry, I believe we're missing potential failures by not targeting these interfaces. And I think it really is, because it's a small percentage of the seam. But as we've shown in this paper, small percentage has significant failure rates. And are you willing to gamble? Um, Obviously, there's benefits to focusing. You catch the holes that are potential bad seams that could compromise the integrity of the geomembrane. And, I really think a call to action for the geomembrane industry, I think we should have guidance that's related to this, as um, both to target interfaces on your original samples, but also your tracking samples. And, you know, all the guidance right now is for less holes, okay, we can reward them less holes in the line or less holes, which less holes is good, but is less holes that much better, or maybe even worse if you're not targeting interfaces that um, have shown that they fail at a higher rate. So that's the thought I'll let you lose sleep over too. So I'm not the only one, but anyway, that's the conclusion. My next webinar, at least as it's titled right now, is going to be best practices in CQA and project oversight. I think there's a lot there. I've been toying with the idea of making it a Halloween theme. So, maybe the title will change, the content stay the same, or I might change the content. There's a lot of things I can, do Nightmare on the Line or part one or something, with Johnny the Welder. Actually, we had a guy we nicknamed the Mangler because every weld he did with his fusion weld and extrusion weld was bad. Yeah, he was another one that shouldn't have been welding, but eventually they pulled him because his destructs failed. But um, anyway, I hope to see you in October. It'll be Thursday, October 16th, same time, 12:30 p.m. Eastern. And with that, questions and answers. If you have any questions, I'll try and take a look here and see if I have any questions. Uh-oh, here we go. Am I still there? I can't figure it out. Where did I go? I did something wrong. Yeah, I was screen sharing. Am I still on? I'm still on, huh? Ah, ooh, there it was. How did I make it appear? Sorry, it's been a long, long week, and I'm tired, but somehow it was up at the top of my screen there. Why can't I make it appear again? Ah, there it is. All right. Let me see here if there's any questions. Um, I'm trying to figure out how to get my screen back here. There it is. All right. Yeah, sorry about that. Like I said, it's been a long week, about 10 days of working around the clock to meet some deadlines. So I appreciate you bearing with me here. I do not see any questions. So um, um, yeah, well, thank you for joining me. I hope I enlightened you with some information, something to think about. Like I said, I don't want to be the only one out there thinking of this stuff at night. And I'll see you in October. Thank you very much. Oh, hang on. Somebody put a question. Oh, hey, there it is. Yeah, Gerald, early in the webinar, I showed a photo where the installer, oh, that wasn't um, textile, Gerald, it was geomembrane. It was a microspike. They flipped it. So, in my opinion, it shouldn't have been flipped because you're changing the friction angle, but the engineer was okay with it because it was only a 30-foot high slope. But that's something you got to keep an eye on the installers. They are, prone to flipping the material. It makes it easier for them to track what came off of what roll because there's a color differential there. But all the calendared manufacturers I've talked to, they said their friction angle is different between the design top side and the bottom side. So please keep that in mind. And I thank you for that question, Gerald. And I guess that's the only question. Um, Okay, yep, that's the only question. So, yeah, thank you very much for tuning in, and I will see you in October. All right, thank you.